Dear all, thank you everybody for listening to this recording. I'm going to talk today about the model selection using the relevant transformation of the inputs network approach, RETINA. And this is a joint work with Hal White, who was my thesis advisor, and regrettably he passed away 5 years ago. Then myself from the University of Complutense of Madrid, Giampiero Gallo of University of Florence, and then Massimiliano Marinucci from the Coca-Cola company. He was my student at the time. We are going to present the version that we showed in Chalmers University of Technology in November 2019. And what I'm going to talk about today is a work that I did in 1999 while I was visiting the University of California, San Diego, and it's based upon original ideas by Hal White, who is and was a very famous and very bright person who had a lot of ideas, a lot of feelings, and a lot of um, results about this area. This area is what is now called big data, and it wasn't called that way at the time. At the time, it just was approximation. We had also neural networks. We had other many different procedures with more or less known words and names. The idea here is that we want to approximate a relationship between one variable and possibly some explanatory variables that may be one, maybe hundreds, and typically there will be a large amount of possible explanatory variables in this area. So we're going to work on the conditional distribution of the variable y on the inputs x's. The idea is to be able to help take decisions that are data-driven and not driven by feelings, eyeball, or other non-scientific ways. This nowadays is mainstream, but at that point it wasn't the case yet. The idea is we can improve on what you measure, and it is important to measure things. So nowadays we have a lot of names for this type of discipline: big data, machine learning, data science. And the idea in this particular case is that I'm going to show you just one procedure because I don't want to just go through many names that may be hollow to you. And the big data procedure that I'm going to tell you about is the one that we constructed at that point in time. And it is going to be useful for data who has high velocity, high volume, high variety, also high number of explanatory variables. And the idea is that there's going to be a fairly large amount of data and a fairly large amount of possible models. We are going to use some tricks of the trade. Tricks are important in this area because you have to be somehow an expert if you want to extract all the possibilities of these techniques. Um, One of the tricks that I would like to start with is the trick by Hal Varian. You know that Hal Varian is a very famous economist. He's a great scientist and scholar. He has been working in the University of California, San Diego for many years. Now he's retired, but he's working since a few years ago as a chief economist of Google. So as a chief economist of Google, you can imagine that he is a very productive, very sensible, and extremely smart person. He's very nice also, and you can find a lot of information about him in YouTube and internet. There are a lot of meeting and interviews, and the last few papers that I have read from him are extremely useful for people who start their careers. Extremely useful. So I encourage you to look at Halvarian and look at his teachings, which are extremely important. So one of his many tricks of the trade here is, instead of analyzing all the data that you have, it is enough to analyze a sample of 1 out of 1,000. So in that way, you reduce the dimensionality of the problem a lot, and then you will be able to deal with data that are huge in number and size in a simpler way. We'll see more of these tricks later in this talk. Here, we only have to tell you also that you have exotic names for different procedures. Most of the procedures are known since the 1980s and 90s, but at the moment, there was not enough computer capacity, and there was not enough storage capacity, and there was not enough samples this big. So that's why the theory has been ahead of the practice for quite some time. Today, again, I'm going to talk in detail about retina, because this is our procedure, and I can show you that it has a lot of nice features that other procedures don't have. Some of the procedures do have similar characteristics to this one, but this is something that I will talk about by the end of the talk. The two seminal papers that we wrote and were published in the Oxford Bulletin of Economics and Statistics and the Econometric Theory, which are very respectable journals, were these two: a flexible tool for model building, and the relevant transformation of the inputs network approach, and then a comparison of complementary automatic modeling methods, RETINA and PC-GETS. So those are the main foundations of what I'm going to talk about today. The general idea is that we need a flexible, out-of-sample conditional forecasting method. So that is our goal. And it has to have some features that make it attractive. One of them is that it has to improve on neural networks, which was at the time the model to beat, and it was developed here in the University of California, San Diego in 1999 by the team that I just mentioned. The general idea then is that we want to approximate. And here in this transparency, you see that we have a Y, which is the blue line, that fiddles around according to the values of X, and we don't know what is that relationship. We just don't know. We're trying to approximate it with some features, some characteristics, and a method that allows us to get an approximation that, say, in this case, would be like the red dotted line, and that would be the approximation. Of course, this looks simple in 2 dimensions. If you have instead 100 dimensions or 500, then the problem doesn't look as easy as it looks in just 2 dimensions. Let us start by talking about retina specifically, and what I'm going to do is explain like you have in an onion, you have a lot of uh, layers. So I'm going to try to explain in layers. First, the inner layers, which give you the basic ideas, and then layers that are bigger and bigger. The difficulties that we have found using neural networks are essentially non-concavity and due to non-linearity of the parameters. And that is a big problem because that means that the computer algorithms never converge or take too long to converge. Another problematic thing is irrelevant predictors. So if you have a lot of predictors that are irrelevant, that do not help very much, but are similar or related to the ones that are included, then we have similar problems. It takes forever to converge. So the estimation never finishes. The computer goes on and on and on all the time. So we need a different modeling approach, which is called RETINA, which has the flexibility of neural networks. It can follow the movements of Y that we have seen. It has the concavity of the usual estimation methods, so it is easy to maximize. And then it has the ability of getting rid of variables that are not really important. So it identifying only a small set of attributes that are useful for prediction. In this transparency, we see graphically what is concavity and what is non-concavity. The upper part is a concave function, and the idea is that it has a well-defined maximum, and it is easy to interpret, and we shouldn't have any problems with that situation. In the lower part, you find a graph of a non-concave function in which finding the maximum is not very easy, and actually there's no maximum in there, meaning that the computer is going to have a lot of problems dealing with that type of data and an installation like this in which there is a relationship between x's and other x's, then what it happens is if the relationship between one x and several other x's is like this we have, the idea is that it is very difficult to disentangle the effect of one x, x1 or x2, or on the other x, and that means that we have problems. It is very hard to discern what is the relevant case, what is the relevant variable. Some of them have very similar information. And that is called multicollinearity, and multicollinearity causes problems of estimation, and that is something that we want to avoid whenever possible. The next idea is what types of models we want to build and why, and which objective functions to use for performing comparisons. The first idea is we want some models that are really flexible. Flexible means that they allow for different functional forms, and what we do here is essentially use transformations of the inputs which are nonlinear in the inputs. However, in the second point here, it says that we want concavity, And we achieve that by using linear models in the parameters. So those are the typical linear models in the parameters that we are going to use all the time, like in most of the time in econometrics. And then the third thing would be that the transformations of the inputs, that we entertain as possible explanatory variables should not be too highly correlated with each other. We should use a parameter lambda just to control for how much multicollinearity we allow in our data set. Then it is impossible to check all variables for that may intervene in the models. It is impossible because we have 2 to the m models, where m is the maximum number of transformations. Say if m is, for instance, 1 million, then 2 to the 1 million is a number which is very hard to contend with, and it is impossible to check that many models. That is why we only will analyze just a few models, and we are going to use a saliency feature for discriminating between models. So we are going to use a criterion, and the criterion is we want models that minimize the sample prediction error. And the idea is that it has to be out of sample prediction error. Those that I just told you are general ideas, and the general ideas can be best seen when applied in a particular example. And this particular example is the one that I'm showing you. I am showing you different values for y and x. X only has 2 components, and then y has 1 component. So this is the very basic example. The idea is y can be the number of sweaters that a person buys along a year, and then x1 and x2 may be the number of income that he has. In x1 may be the income, a measure of income, and then x2 may be a measure of price of the sweaters. Sweaters are sweatshirts. I don't know how you call them here. And the idea here is you start with just 2 variables, but you want flexibility, and the flexibility is going to be given to you by using a specific kind of transformations. The transformations are the W's. W1, x1, x2, x1, x2 is the cross product, and then the squares of 1 and square of 2, then the inverse of 1, the inverse of x2, then x time plus the inverse of x2, x2 plus times the inverse of x1, and then x1 to the minus 2, x2 to the minus 2, and then x1 to the minus 1 times x2 to the minus 1. Those are arbitrary transformations that you may think that they are useful. If you don't like them, you may think of other transformations like taking logarithms or taking square roots or any other transformations, linear or nonlinear. And so that's up to you to decide which ones you like. Then the next part is using those W's and putting them together in a vector and call them W1 through W13. W means whatever, And whatever means that whatever transformation you have done, you can include it there and then take it from there to build a new model. Once we have done the transformations of the original inputs, the second step would be to divide the sample into 3 parts. The 3 parts are going to be essential because in one part we are going to propose a model. In the second part we are going to estimate a model. And in the third part we are going to choose a model. What we do then is, as you see in the next transparency, we divide the subsamples. We assign them randomly into 3 subsamples that may have a similar size but not necessarily the same. What we can do then is we estimate the sample univariate correlations between Y and W's, and the idea is that you do that to assess the importance of each of the W's, each of the candidate inputs. If you do that, what you get is a here you see the sample of size n divided in 3 parts. What you do is essentially with those correlations that I'm talking to you about is sort the W's by rho hat sub j in absolute value. That means you sort the W's by its importance. And importance means absolute value of the correlation with the dependent variable. This is something normal. It makes sense. It makes sense just to not to treat all the variables in an equal footage. They are not equal. Some of them are more important, others are less important. And in this case of economic data, it is very useful and very important to. In this transparency, we continue with the previous process, and what we do is try to build models that are based upon the previous importance criteria, and that means selecting not all the variables that we have constructed, but only those that allow for little collinearity, meaning that we don't want variables that are redundant in terms of forecasting. So what we do first is we choose a lambda that is 0, and then we only have one independent variable, W. Then the lambda can be equal to 0, and then we will have like only 3, 1, 2, and 9. Then lambda equals 0, 2, and then the model will consist of variables W1, 2, 5, 6, 9. So what it is saying you is the more multicollinearity you allow, the bigger the complexity of the model. Now, what we do with those proposed models, we estimate each model in subsample 1. In the first one, we are still in subsample 1, and then select a model which minimizes the mean square prediction error in the second subsample. Okay? And so this is one first cross-validation. And then you estimate the submodels of this particular model that you have just chosen in subsample 2, and go to subsample 3, do the out of sample prediction there, and choose the model with the lowest cross-validated Akaike information criteria. So that is another way of penalizing the models so that they are not too big. What I just told you about RETINA is very specific because it is only just like a little example. But in general, you can do more than that. You can do a lot of things with RETINA. You can have more flexibility. And then what we do here is, in this section 3, is be more specific and also more general in some cases, and give you more details. The first thing we do in RETINA is we have candidate predictor attributes. Well, the X's are potentially a very large number. We are now working with a database in which the X's are 750. They are quite a substantial number. Of course, the first thing we are going to do is to cut down this big number to maybe 100 or so, which is much more manageable. Then from the excess, what do? We construct different W's, and those W's are essentially the products, cross products, inverses, ratios, and all this. But of course, those need not be limited to beta equal to -1, 0, or 1. They can go higher, and also and those can be logarithms or other transformations that you would like. Then the next thing we do is we split the sample in 3 disjoint subsamples, and that is going to be great. It's going to be very important because you really need the 3 subsamples. In subsample 1, you compute the univariate correlations and then rank the W's, as I told you, then proceed with along the W's using linear regressions on that, and then obtain a candidate models that can be estimated, as I told you in the previous transparency. Then what you do is you repeat that exercise by different values of lambda. At the beginning, we thought that lambda would be crucial and essential. After several uses, you see that lambda doesn't change that much the choice of best model. So lambda is not that important. You can use quite a very few values of lambda just for making sure that there is no extreme multicollinearity. But it is reassuring that lambda is not that important. And then we select the best choice model by minimizing the prediction mean square error, and then go to the third, that is in the second subsample, and then go to the third subsample and do the cross-validation. In that case, you will choose the model that gives you the lowest Akaike information criterion in subsample 3. So that is the whole thing that you need to do and you need to know. Nothing that I have said is mysterious, is strange, it's a black box. Everything is absolutely transparent. One thing that I wanted to tell you now is that we want not to use not only samples 1, 2, 3, but also 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. And the reason is that the outcome in terms of the best forecasting model in the previous step may just not be robust to the choice of samples. And that is why we do this additional exercise. That means repeating the previous procedure 6 times to avoid the possibility of having making a wrong choice in terms of the best model for out-of-sample forecast. I want to comment also that this paper has some related research, and there are several of the ingredients of retina were already present in some of the previous literature. You see here like Miller, Shaw, Brayman, Zhang, and Hasty and Tifshirani, Brayman and Friedman. So there are a collection of different other procedures. All the procedures have pluses and minuses, and you have to think that there's no best procedure because that depends on which time of data. Medical data are not the same as other biological data, engineering, economics, sociology. They are different types of data. And for different type of data, there are different types of best quote unquote procedures. I'm not going to go in detail through the transparencies here, but I do want to tell you that there are several ingredients in common and with other procedures like the exhaustive search is impractical for Zhang, and he does a selective search. So that's interesting to know that this is not an isolated um, procedure, but rather has a lot of cousins around there. The simulations that I would like you to think of are the following. See, once you have proposed a particular procedure, then you have to see whether it does well or not. The first trial that we need to do is the simulations. Why? Because this is like a particular and minimal type of situation in which you need the procedure to work well, at least in data that are generated in the way that you know they are generated. So that means you generate data and then try to apply the procedure, the retina procedure, to find out whether the retina procedure is good or bad for that particular set of data. We have done a lot of simulations, and the simulations essentially means that you create data once, twice, up to 10,000 times, and then figure out in how many of those trials the data come out well. The procedure does a good job. So that is the idea for the Monte Carlo simulations that we have done. That is the way they are called. And we have done with the data generation process is controlled by us. The data generation process is linear in the X's, for instance. Then another type of data generation processes is nonlinear in the X's. Then we have explanatory variables that are discrete in some cases, data that are sparse, meaning that there are very few data available. And then you have outliers, so that means that there are several points of data which are very far from the rest. They may be contaminated or maybe wrong, wrong way of thinking, whatever. So the design of experiments is, as you see here, I'm not going to go through all this because it takes a few minutes that we don't have, but I do want you to see what are the outcome of the experiments in terms of graphs. You see, in figure 1, you have a particular way of generating the data, which is a linear case, and then I would like you to look at the blue line. The blue line is the one in which the R square is 0.75, And then you can see that as the number of observations increases, say as it goes up to 1,000, then the number of successes increases likewise. Okay, so it is very important to see how this graph goes. In the next graph, in figure 1b, you see this is the type of outcome that you will get if you use an alternative procedure, which is called non-negative garrote. And that garrote is an instrument of torture for killing people in Spain. And of course, the garrote is not is developed by people in the United States. It's just fun to call it garrote. But what this does is it shrinks the experiments, shrinks the coefficients to make them smaller and smaller. This is not doing very well here because the environment, natural environment for this garrote procedure is not the one that we are dealing with. In economics, typically we have a, a few parameters and large parameters. And in other sciences, you have a lot of parameters, maybe hundreds of parameters, but very small. So garrote does worse essentially because it is designed for a different situation. In other cases that we have followed, we have used the same uh, type of data generation process as in the previous case, but we have, as you see, very high performance when n is 1,000. But please notice that these uh, procedures, big data procedures, really need much more than 1,000, maybe 1 million or 10 million observations to really be working well. But in this case, just having 1,000 is doing quite well. If you look at the blue line and you look at the 99.5 in the upper part. So that is quite successful. Then if you have nonlinear transformations, you go to situations that also have a very high number of successes without any problem. The same is for products. You have a cross product of x1 and x2 as the real data generating process. It is very easy to calculate. If you have dummy variables, which are variables that numerical variables that allow to use categorical information in the data, that would be a linear with dummy. You see there are also high rates of success. You also with sparse data, less successful, but still very successful, especially if you think that 1,000 is very few observations. Again, outliers give you very high possibilities of having good behavior. Mm, the another type of outliers also work very well. Um, then the structural breaks are also captured very well by the different cases. And so let me jump to the conclusions. The conclusions are that retina works reasonably well, especially if you compare them with different other procedures, like for instance the Hoover and Pérez LSC methodology framework and the Shao framework also. So they compare well, but I'm not saying that it is the best. The discussion is that it's a complementary to other data analysis techniques. It is exploratory, it is modular, and that is very important because you can check and change things if you don't like what they are doing in a particular modulus. And then it is an idea of going from general to more general and then to a specific approach. And the idea would be that the sample sizes required are not very big. And so the general conclusion is that it is useful for applied researchers if you would like to use it. Um, just to illustrate how mm, how much what are the numbers that are involved here. Uh, one idea is you have 10 x's. Those 10 x's generate 181 w's, and that means 3 times 10 to the 54 models. You see, 10 to the 54 is a number that I cannot pronounce. I don't know how to say it in English or in Spanish, no idea, because it's a huge number. And 10 is very little. Even 100 is very little. So the number of models that one is considering is absolutely huge. It's very important to notice that that is why it is called big data. Also, it's not only that the quantity of data is high. It is not only the variety. It's not only the volume. It is or the velocity, it is the number of possible models that make the big data. And then the last transparency that I want to show you is this one, in which you have the HTTPS address, in which you can look about Retina, look about manuals on Retina, and download Retina for installing it in your own computer if you would like. It would be a simple and painless way of entering the world of big data if you haven't done that before. Okay, thank you very much, and I hope that you have enjoyed the presentation.